Well, when we thought up the rare earth hypothesis, it was simply taking a look at what happened on this planet that allowed us to have multicellularity. Part of it was that we had conditions allowing habitability for billions of years. It took a long time to get to something as simple as a two-celled creature. A long time. How do you get a long time? You do it because systems of temperature, systems of oxygen, systems of all the gases and the carbon movement remain stable. If you get too hot, too cold, and only a little bit too hot and a little bit too cold on a planetary sense, you kiss it all goodbye. So what is it about the Earth that allowed those things to continue for such long periods of time? The most important is plate tectonics. This is the movement of the surface of the Earth over the top of a mobile, softer rock substrate beneath it. So the continents skate around like bumper cars. But part of that process is a continental and an ocean recycling. And that recycling system is inherently, it's the absolute necessity to keeping long-term temperature constancy. We have this feedback system, a thermostat system. What makes the Earth warmer is carbon dioxide. What makes the Earth cooler, interestingly enough, is the removal of that carbon dioxide. Volcanoes put it in the air, but weathering removes it. If you take a granite or any rock that had volcanic material in it and let it chemically weather, one of the byproducts takes CO2 out of the atmosphere. The warmer it gets, the faster that process works. And so the warmer it gets, the faster the breakdown removes CO2. If you get down to an area or a level at which you no longer chemically weather, the volcanoes refill you up. Now that bang-bang feedback system has been in service here for over 3.5 billion years or more. That has kept us at a stable temperature. How often does a planet have plate tectonics? By looking at the nature of the rock, we barely have it. If you want to think about the end of the world is going to happen when the coefficient of sliding rock, when the friction coefficients overexceed the type of rock we have, we no longer have these subduction zones. The end of the world is also going to be when our core, we have this liquid molten core, it's going to freeze because the Earth is slowly dying and cooling. When that freezes, we lose our magnetic field. And so we also have consequences for plate tectonics. Losing the magnetic field, losing plate tectonics will definitely be the end of life on this planet. And so those two things are geologically produced. How often do you find both of them in the same planet? Theoretical studies say not very often. What if we didn't have a good Jupiter but had a bad Jupiter? Well, then you can really kiss it all goodbye. A highly elliptical Jupiter ends up either causing the inner planets, the rocky Earth-like planets, to be ejected into space or pushed into the star itself. I mean, obviously that's a death sentence either way. You've got to have a good Jupiter. The other complete unknown is how much ocean do you get from asteroids coming in? The oceans we have on this planet are a byproduct not just of water on the Earth when it was formed, but lots of comets that came in early in Earth history. Now, if we have too much water, let's say we had an additional ocean, to the point that we don't have land sticking out of the water, well then this feedback system, the temperature system doesn't work. You've got to have, what's really scary is that you might have to have ocean-land mixes of this 2/3, 1/3, or even half-half to make the whole system work. You have to have rock out, you have to have oceans to have water, but how much of each? And the modeling is just starting, and it's a little spooky. And it really does look like there's not going to be a lot of Earth-like planets. Let's take the last part, our moon. Here's the scary deal. So in Caltech, new calculations, let's say we have no moon. And obviously looking at this solar system, Venus doesn't have a moon like ours, Mars doesn't, Mercury doesn't. We're the only one that has an Earth-like planet with a moon that's an appreciable size of the planet itself. If that moon is not here, our day is 4 hours long. 2 hours of daylight, 2 hours of dark, 2 hours of daylight. Our spin rate increases so much. The moon is a brake on our spin. What happens to climate when you have a spinning Earth that has a 4-hour day instead of a 24-hour day? The entire climate system, radically different. Would it sustain life as it does now? Well, the models are just kicking in, but this one itself might actually have been something hugely important in allowing there to be as much complex life as there is now. Well, the Kepler missions, the satellites that are going to go out there and tell us how many Earth-like planets there are by blotting out images of the stars that are near so we can actually see disks. What's interesting now is an Earth-like planet it looks like Earth is on the small end of what we now call Earth-like planets. We're seeing far more what we call super-Earths, which are about 2 times Earth, but they have a lot more gravity. There's going to be no way you would have complex life of our shapes and much higher gravity. You're certainly not going to have things flying around as we have. You would probably have different shapes of fish. You could get complex life, but it would certainly not look like the stuff we have now. It's just from the physics, the differences in water and air.